80 degrees Celsius. The air is now compressed. The air is compressed to 0.1 meter cube in such a way that the temperature inside the cylinder remains constant. Now determine the work done during this process. Okay, so again, the concept over here is like this. Please, all the time, try to understand the nature of the question. It's very, very, very important that we understand the nature of the question. And it is like this. Let us try to sketch it. We have a piston cylinder. Yes, I'm going to use the same cylinder. So a piston cylinder arrangement like this. Okay. And then the piston is compressed. Okay. But you know that whenever there is a compression taking place, okay, so we have an ideal gas trap in this cylinder, and then we compress it. The moment you compress the air, the ideal gas, the air inside the cylinder, its temperature is going to increase. How does the temperature increase? Because the piston is going to impact some energy on the fluids. So in this way, the temperature of the fluid is going to increase. But we are told that this particular experiment was conducted such a way that the temperature in the cylinder remains constant. So how do we ensure that the temperature as the piston is being compressed downwards? Okay, so naturally, when the piston is being compressed downwards, the temperature increases because of the fact that the molecular energy of the individual fluids also increases in this way. But here we are told it's a constant temperature. So it means that when the piston is being compressed, okay, so the temperature remains constant because we continuously to take some Q out of the system. You understand me? So it's like you go to the gym, you lift some weight in order to burn some calorie. So, but as you lift the weight, then you are consuming some more, let's say, sweet or some, what do you call it, some food. So as you burn the weight, as you lift the weight up, you burn some calorie, but immediately you are replenishing the calorie by taking amount some food. You understand me? So your calorie, by the time you come out of the gym, your calorie will remain the same. The same thing is situation is happening over here. So this is what we call, it is not a constant pressure process. It's a constant temperature process. You understand me? So it's a constant temperature process. The temperature remains constant throughout the experiment. So we are told to determine the work done during this process. So if you don't understand this, and then you say, oh, the work done is given by, so we know generally that the boundary work is defined as what? Integral of P of dV from 1 up to state 2. This equation is valid only for constant what? Pressure process. But for a constant temperature, for a constant temperature process, or a constant temperature process is the same as what? Isothermal process. So it means that we have to know what is the appropriate equation for isothermal process. Immediately, you have to tell that the boundary work for isothermal is given by P1 V1 log of V2 divided by what? V1. You understand? So this is very important. If you don't take time and then you go and write W equals to P dV. P dV is only associated with a constant pressure process. You understand me? So the pressure and here we are only told that the temperature of the fluid remains constant. So for a constant temperature process, the boundary work is given by this. So now we know the value for P1, we know the value for V1. Now we need to determine what? V2. You understand me? So how do we determine V2? Knowing that what is the working fluid? Working fluid is what? Ideal gas. Working fluid is ideal gas. Again, don't tell like this that it is water or refrigerant. So here we cannot use the property table. We will use the ideal gas. So we know the value for P1, we know the V1, but we don't know V2. How do we determine V2? Using the ideal gas equation. So because of the fact that from ideal gas equation, from ideal gas law, we know that, so from ideal gas law, P1 V1 equals to, sorry, P1 V1 equals to MR T1. Similarly, P2 V2 equals to MR T2. Okay, so if I divide this by this, I divide this by that, MR will cancel MR. Temperature for isothermal, T1 is the same as T2. So this and this will cancel out. Immediately, we will have P1 V1 equals to P2 V2, like this. Okay, so now let us see. So down, the cylinder device initially contains 0.4. Oh, sorry. So we know V2. V2 is given already. Sorry. It is P2. Let me see over here. So the question is much easier then. So there's no need for us to even go to this length. Okay, so we know the final volume of the cylinder. Okay, so initial volume is this, and then the final volume is given by this. So I think there is no need for us to determine P2. Okay, so let's say if you want to find P2, then P2, assuming P2 will be equal to P1 V1 divided by what? V2, like this. So we know P1, we know V2, then we can find P2, the final pressure. Okay, so but even this is not necessary. So quickly we will tell the boundary work equals to P1. Okay, so P1, the initial pressure is given by 100 kilopascal. This is 100 kilopascal times the volume, V1, which is 0.4 meter cube, times log of V2, which is V1, sorry, 0.1 divided by 0.4. Okay, so you have to find the work done from here. Okay, cool. So can somebody calculate this for us? What is the final answer? Yes.
So it possible to be negative
What?
or not? Possible to be negative or not?
Yes, of course. It can be negative.
Negative 55.
Negative 55.
0.45.
Point what?
452.
452 kilojoules. And the reason why it is negative, you see, I've told you, in the sign convention, you see, we are compressing. So this is given by boundary work, which is the same as W in. I've told you, whenever, let's say on the PV diagram, it is even given on the PV diagram. The fluid is undergoing compression. So volume will be reducing, pressure will be increasing. So it is going in this way. So this is state 1. This is the final state. You understand me? So that over here, whenever you compress an ideal gas or any fluid, so the sign convention is such a way that W in is always a negative quantity. And whenever you have W out, it is always a positive quantity. You understand me? So don't be discouraged or be frustrated that, oh, I got negative. So it's possible. You understand me? So this is correct. And this shows that work is coming into the system. If the system delivers work output, then it is positive. If the system receives work input, then it's a negative quantity. So this is correct. Okay, so any other question? Okay, so we move on to the next question. Let's see. Okay. So the next question is this. So 3 points, let me see, 3.6. 3.6 we have just done already. Okay. Okay, 3.5, we are just finished. So 3.6, this is the question. So this is question 3.6. Okay, so here we are told that a cylinder, in the cylinder of a large engine, 1 kilogram of carbon dioxide at 527 and 20 bar expands isothermally, okay, to a pressure of 1.4 bar. Now determine the final volume of the gas. Okay, so again, this is isothermal. We want to determine the final volume of the gas. So now, in this particular situation, mass of the gas is given 1 kilogram. Okay, this is carbon dioxide. And then initial temperature equals to final temperature, which equals to 527 plus 273. Okay, so Kelvin, this way. And then, so let's see, P1 equals to 20 bar, which equals to 2,000 kilopascal. And then P2 equals to 1.4 bar, which is the same as 140 kilopascal. Want to determine the final volume. Okay, so this is very easy. Here we are not interested in the work done. The question did not say find the boundary work. If it says find the boundary work, then again it is going to be P1 V1 log of V2 divided by V1. But the question did not ask for this. So it says find the final volume. So we only apply the ideal gas equation. So from ideal gas law, P1 V1 equals to MR T1. P2 V2 equals to MR T2. All this will be constant because T1 equals to T2. You understand? So now, eventually, we'll have P1 V1 equals to P2 V2. Okay, so and we are interested in V2 equals to P1 V1 divided by P2. Okay, so that's all. Just substitute all the parameters inside. Okay, you know, and the P1 is, let's say, 2000 divided by 140 times what? V1. So V1 is giving, oh, sorry. So we don't know V1. So how do we determine V1? Very important. Yes, so this is very tricky. So how to determine V1? Let's say this is our V1. So V1 can be determined from ideal gas law. So P1 V1 equals to MR T1. Okay, so I'll say my V1 equals to MR T1 divided by V1. Sorry, divided by P1. So this gives me mass of the ideal gas is known. Okay, so we know the mass of the ideal gas, 1 kilogram. So 1 kilogram. And then the ideal gas constant for air. So who can tell us the ideal gas constant for air? I think it's about 0.287, if I'm not mistaken. Okay, ideal gas constant for, oh, it is carbon dioxide. I'm very sorry. It's not air. So we have to put the ideal gas constant for carbon dioxide. Ideal gas constant for carbon dioxide times the temperature divided by P1. Okay, so let's see. Okay, so let me see. Nobody has given us the ideal gas constant for carbon dioxide. So now I'll leave this to you in any case. So you put the mass there, the ideal gas constant for carbon dioxide, temperature, and then T1, then you can find V1. Then if you finish, you substitute the value for V1 into this equation to find V2. Okay, that's the final volume.
0.1889.
0. Point what?
0.1889.
So 1 kilogram times 0.1889. Okay, times 527 plus 273. So how much is this? Divided by P1. P1 is, let me see. P1 is 22,000. Okay, so what is the final volume? V1. What?
$75.56.
How much?
$75.56.
75.56. So meter cube. So now we'll substitute into this equation now. Okay, so that gives us V2 equals to 2000 divided by 140, 75.56. So what is this?
1079
1079.43.
79.43.
Thank you. Meter cube. Okay, so that is it for this question. So next question, yes, 3.7. 3.7. Okay, so we have air at 20 degrees Celsius in a cylinder of a diesel engine. Is compressed from an initial pressure of 1 atmospheric pressure, 1 atm, and volume of 800 centimeter cube, okay, to a volume of 60 centimeter cube. All right, so then assume that the air behaves as an ideal gas with K equals to 1.4 and that the compression is adiabatic. Find the final pressure and temperature of the air. Okay, so here we have a cylinder that is undergoing a compression process. Okay, so we have a cylinder. So we have a cylinder like this. And then initial position T1 equals to 20 degrees Celsius. So V1 equals to 800 centimeter cube. Okay, so this gives us how much? A meter cube. So this gives us 800 10 raised to the power minus 6. Okay, so meter cube. And then, so the fluid, it is compressed. The fluid is compressed. So this is state 1. And then it moves to state 2. As state 2 volume is reduced. And the final volume V2 equals to 60 centimeter cube. Okay. So now, which is the same as 60 10 raised to the power minus 6. Okay. Then we will have the value for K is given. Now be careful over here. We are told like this, air at 20, initial temperature of the air is this. And then the cylinder, so in the cylinder of engine is compressed. So this is compressed from an initial pressure of 1 atm. Yes, so it means P1, 1 atm, which equals to 100 kPa. So, and then the initial volume is given, and then the final volume. I assume that the air behaves as an ideal gas with K equals to 1.4, and that the compression is adiabatic. So if the compression is adiabatic, what does that mean? First thing that has to come to your mind, that What is the meaning of adiabatic? So adiabatic means heat is not allowed to flow in and out of the system. You understand me? So be careful. Don't confuse yourself with adiabatic, and isothermal. They are completely different situations. Adiabatic means that there is no heat. The net heat equals to 0. You understand? Net heat equals to 0. Whereas for isothermal, it means T1 equals to T2. So here, for adiabatic situation, it does not mean that T1 equals to T2. Don't say like this. This is not correct. You understand me? Even though the compression is being compressed, or the fluid is being compressed adiabatically, temperature can increase. You understand me? Even though heat is not allowed to go in and out of the, and it is true that when the process is being, or when the fluid is being compressed from initial state up to the final state, temperature of the fluid increases because the system is not allowed to exchange heat with the surrounding. You understand me? So we have to determine the final pressure and final temperature of the air. So what we need to do over here, I've told you last time that all adiabatic processes are the same as isentropic process. You understand? So isentropic process. And all adiabatic processes obey the law PV raised to the power K equals to a constant. You understand me? So for adiabatic process implies that PV raised to the power K equals to what? A constant, equals to C. It means P1 V1 equals to C. If the system is undergoing a change of state from state 1 up to state 2, so still then the system is undergoing a change of state, let's say from state 1 up to state 2. Okay, so it will follow the same law. Means that at state 1, we will have P1 V1 equals to C, and at state 2, we will have P2 V2 again raised to the power K equals to constant. So these constants are the same. So we have P1 V1 raised to the power K equals to P2 V2 raised to the power K. So first thing we are interested in, the final pressure. You understand? Final pressure. So final pressure means P2. So what is P2? P2 gives us P1 V1 raised to the power K, all divided by V2 raised to the power K. Okay? So according to this question, we know P1, V1 is known, V2 is also known. We know the value for K. So if this equals to P1 into bracket V1 divided by V2 raised to the power K. So this gives me, so P1 I know, 1 atmospheric, 100 kilopascal. So then our V2 is 800, V1 is 800 centimeter cube divided by 60 centimeter cube, all raised to the power K. K is 1.4. Okay, so now if you calculate this carefully, you discover that P2 equals to P2 equals to 375.7.63 kilopascal. So now we want to find the final temperature. How do we determine? You see, even though this experiment is being conducted under adiabatic condition, temperature is changing. You understand me? So you have to clearly understand between isothermal. Isothermal means that it's a constant temperature process, which is completely different from adiabatic. Adiabatic means heat is not allowed to flow in and out of the system in this way. So now we will find, how do we determine T2? T2 can easily be determined from ideal gas law. So ideal gas law, again, is valid generally for all situations, for all ideal gases, irrespective of the state, either state 1 or state 2. Ideal gas law is valid over there. So let's say P2 V2 equals to MR T2. Okay, so now let's see over here, and then we have also P1 V1 equals to MR T1. We are interested in T2. Okay, so either we use this equation as it is like this and tell that T2 equals to P2 V2 divided by M times R. Okay, that depends on if we know the mass of the ideal gas. So the mass is not given. Okay, the mass of the ideal gas is not given. So there is no way we can use this equation. So it means we have to combine the two equations. So by dividing P2 V2 divided by P1 V1 equals to MR T2 divided by MR T1. Okay, so here this and this will cancel out. Okay, so now my T2 equals to P2 V2 divided by P1 V1 all times what? T1. Okay, so if you solve this carefully or clearly, then we will find out that T2 equals to 825, okay, 0.74 Kelvin. Okay, so assuming that we want to determine the boundary work, so the boundary work for adiabatic, so boundary work for adiabatic. It is different from boundary work for isothermal. Boundary work for adiabatic is WB equals to P2 V2 minus P1 V1 divided by 1 minus K. Okay, so you just substitute and then you get a value for the boundary work. Okay, so and that is it for this particular question. Let's move on quickly. Yes, so question 3.8. So maybe I'll explain only this question and then you can try your hands on it. So it is similar to what I have discussed now. Okay, so I'm not going to, I'll just explain. Here again, we are told the temperature and pressure of argon gas inside 0.05 meter cube piston cylinder. So same thing, piston cylinder. We have piston cylinder. So initial volume V1, 0.05 meter cube. At temperature 160. And then pressure P1, 180 kPa. If the argon gas is now expanded, you see, So expansion means we have work given out, W out, which is always a positive quantity. Okay, so means at the final state, we have expansion, W out is the same as the boundary work. If the argon gas is now expanded polytropically to a state of 95 kilopascal, so means the final pressure, P2, equals to 90 kilopascal, and then 90 kilopascal, kPa, and then T2, 110 degrees Celsius. Determine the boundary work, okay, during the process. So what is boundary work for polytropic? It is the same as, similar to boundary work for adiabatic or isentropic. Okay, so a polytropic obey the law, polytropic obey the law, PV raised to the power n equals to constant. Whereas adiabatic, PV raised to the power k equals to constant. This is for adiabatic. Be careful, eh? This is for adiabatic. So that, again, we want to find a boundary work. Boundary work for polytropic, it is given by P2, V2 minus P1, V1, 1 minus N. You understand? So we have to subtract from N in this way. So now, let's see if we know the value for P1, T2, T1, V1, P2, then we can determine the boundary work. Okay? But be careful over here. V2 is not known. So we can determine V2. How do we determine V2? Since we know that a polytropic process is bounded by this law, polytropic, P1, V1 raised to the power n equals to P2, V2 raised to the power n. Okay, so we are interested in determining the value for this. I'm sorry, it is going to give us the value for n. Okay, so from here, let's see, we can determine this particular parameter. Okay, let's say here our V, let me see over here. Yes, so V2, let us first find, and we don't know the value for n either. Yes, the value for n is not given. Okay, so we have to first of all find the value for V2. Okay, but one thing we should know is that at state 2, we know the temperature and pressure. So we can simply tell P2, V2 obeys also the law MR T2. So I can say V2 equals to MR T2 divided by P2. So this gives me, over here, we need to determine the mass is also not known. So if the mass is not known, then V2 cannot be calculated. So it means we need to go back again to find the mass. So mass can give us also from ideal gas P1, V1 equals to MR T1. Okay, so it means that mass of the gas M equals to P1 V1 divided by R T1. So R is the ideal gas constant for argon. Okay, so if you calculate this, mass equals to 180 times 0.05 or divided by 0.2081160 plus 273 Kelvin. Okay, so the mass of the ideal gas gives us 0.0998 kilogram. So now we will substitute this into V2 to give us 0.0998 into bracket. The ideal gas constant for argon, 0.2081. Okay, then into bracket, 11, that is a 0. Okay, the temperature, so 273, all divided by 90. So V2 equals to 0.0885 beta cube. Okay, so this is our V2 now. Now we need to determine the value for N. How do we determine the value for N? Using P2 V2 N equals to P1 V1 N. Okay, so if you substitute all the parameters, you have 90 into bracket 0.885 raised to the power N, okay, equals to 180 0.05 raised to the power N. So if you take the log on both sides, then you have 2 equals to 1.77 raised to the power N. So log on both sides, log 2 equals to N log 1.77. So means that N equals to 1.214. So from here we can determine the boundary work. Boundary work WB equals to P2 V2 P1 V1 1 minus N. So this gives us 4.8 kilojoules. Okay, so that is it for this question as well. And let's move on to the next question. Yes, so this one is a bit tricky, so let's see. So question 3.9, we are told sketch the PV diagram showing the following processes in a cylinder, piston cylinder arrangement. So what we need to do, let's see, we are told initially process 1 to 2 is isobaric. What is isobaric? Constant pressure process. So isobaric process means from 1 up to stage 2. Constant pressure. Okay, constant pressure from an initial volume. Okay, sorry, constant isobaric work output of this from an initial volume of 0.028, and then and pressure of 1.4 bar. So it means the boundary work for 1 to 2 equals to 10.5 kilojoules. Similarly, V1 0.028 meter cube and P1 equals to 140 kilopascal. Okay? So now we have again isothermal compression. So isothermal means compression means the volume is reducing, but isothermal line is represented by this. Okay, this is isothermal. Okay, so that is from 2 to 3. And then the final process, isochoric, means constant volume. Back to the original state. Okay, isochoric to its original volume of 0.028. Okay, now determine the maximum volume. So what is the maximum volume? Vmax equals to what? V2. So V2 will be the maximum volume in the cylinder. Okay, so how do we determine this maximum volume? We need to consider process 1 to 2. Consider process 1 to 2. Process 1 to 2. So in process 1 to 2, this is isobaric. So for isobaric, we have P V2 minus V1. And we are told this equals to 10.5 kilojoules. So we know the final pressure. Okay, we know the pressure, 140. We know the initial volume, so we can find V2. So we have 140 into bracket V2 minus 0.028 equals to 10.5 kilojoules. So V2 from here gives us, if you calculate this carefully, that gives you 0.103 meter cube. Okay? Now we want to determine the isothermal work. Isothermal work. What does the isothermal work mean? Isothermal work means isothermal work. So this gives us W. Isothermal means constant temperature. So W equals to, by definition, we have P1 V1 log of V2 divided by V1. Okay? So but if we look into our diagram, okay, if we consider this to be our PV diagram, this to be our diagram, this is state 1, this is state 2, this is state 3, like this. So this is the isothermal. Isothermal. So it means that the actual definition according to the diagram is given by this. So P1 will give us, this is P2 V2 log of the final volume, which is V3 divided by V1. Okay. Okay, so here, if we know P2, V2, and then V3 and V1 are the same. You see, constant volume, isochoric. V3 and V1 are the same. Okay, so then we will have, let's see over here. Okay, so this gives us O. So what I did over here, this is supposed to be V2. I'm very sorry. This is supposed to be V2. Very sorry. So this is supposed to be V2. Supposed to be V2. Okay? So that we know V2 already. V3 and V1 are the same. So this gives me P2, let's say, the final pressure, P2 and P1 are the same. So I will say I'll have 140 times V2, which is 0.103, then log of V3. So V3, let's see over here, is the same as V1, which is 0.028. Okay, all divided by V2, 0.103. Okay, so if you calculate this carefully, then let's see, you will get the result to be minus 18.78 kilojoules. Okay, so this negative sign again indicates work is done against the piston. You understand? So that's the meaning of that. Now we want to find the work done. The next question, the network. When we say network, W net equals to W12 plus W23 plus W34. Oh, sorry, plus W31. Very sorry. Plus W3 back to 1. So now we know W12 already. W23 is calculated. Now I want to determine W31. W31, this is what? A constant volume process. And for all constant volume processes, we mentioned that the PDV work, which is V2, or let's say V3, the final volume, V1 minus V3 will be equal to 0 because V1 is the same as V3. You understand? So over here, our net W equals to, we have 10.5 minus 18.78 plus 0. Okay, so that gives us minus 8.28 kilojoules. Okay, so now let's see. I think we have done with this question. Yes. So at the network we have calculated. Now the next question, we have to, let us attend to this particular question. Very important. Then we will look at the first law of thermodynamics part, its application. Then we will stop and continue the next time. Okay. So here we have question 3.10. Okay, a fluid at 4.5 bar, 4.15 bar is expanded reversibly according to the law PV equals to constant. Okay, reversibly according to the law PV equals to constant. So one thing that has to come to your mind whenever you are told that PV equals to a constant, what does that mean? It implies that if you look into the ideal gas equation, PV equals to mRT. So it means if you want to compare this equation with this, it means for C to be constant over here, then it means M must be constant, R is constant, all this M is already constant, R is also constant, then it means T also has to be a constant. So it means the whole of this has to be what? Equals to a constant. And if the whole of this is constant, it means the process is what? Isothermal. Isothermal process. So there is no way in which we can have PV equals to C, which is not isothermal. It is isothermal because it's a constant temperature process. If it's not a constant temperature, then we cannot have PV equals to C. So this is the indication. So you see that in this particular question, we give you the equation instead. So we expect you to come out and tell that this process, that is the law PV equals to a constant, is an isothermal process. Similarly, if I have, let's say, PV raised to the power n equals to a constant, this is a polytropic process. And then if I have PV raised to the power k equals to a constant, it means this is adiabatic process. Or sometimes it is also called isentropic process. Okay, so clearly the question is very straightforward in this way. Okay, so now again we are told that so the fluid expands reversibly according to the law PV equals to constant to a pressure of 1.1 bar. So there is expansion. And how do you represent isothermal process on a PV diagram? Isothermal processes is generally represented by this. So if we have to draw the diagram, let me delete this. If you have to draw the PV diagram over here for the process. Okay. Initially, we have isothermal is normally represented by this. Oh, sorry. Isothermal is normally represented by this. Okay? So it means from state 1 up to state 2. This is isothermal. Then we are told P1 equals to 4.15 kilopascal, sorry, bar. Okay. So this is bar, and then P2 1.15 bar. Okay, and the pressure of this until it has a specific volume. So V2 similarly, specific volume V2 equals to 0.15, 0.12. So this thing is misbehaving. So P1 4.15, P2 1.15, and then specific volume V2 0.12 meter cube per kilogram. So it is then cooled reversibly at constant pressure. So cooling reversibly at constant pressure up to stage 3. That's it. Okay. Now, then it's cool again at constant volume. Okay, so constant volume cooling means like this up to the final volume. So this is state 4. And then it is then allowed to compress reversibly according to the law PV. Which law is this? PV raised to the power n. This is polytropic. Polytropic. So polytropic means, again, you have a situation like this. Okay, so this is the whole diagram. Now, the work done in the constant pressure process means the boundary work BW 2 to 3 equals to, this gives me 0.525 kilojoules. And then the mass of the fluid, mass of the ideal gas, 0.22 kilogram. Calculate the value for N in the fourth process. So this process is isothermal. This is constant pressure, isobaric. This is isochoric. And this is polytropic. Polytropic process. Okay, so we want to calculate the value for N in the fourth process. Okay, so very clear. Everything is now clear to us. So now we need to determine the value for N in the fourth process. So, but we all know that the fourth process is governed by a polytropic situation. Okay, so for all polytropic processes, process, PV raised to the power N equals to a constant. So it means if we have P3, if you consider process 4 to 1. So then we will have P4, V4 raised to the power N equals to C, still P1, V1 raised to the power N equals to C. So CC means P4, V4, N equals to P1, V1, N. So we are interested in determining the value for N. Okay. So from here, we can say like this, that P4 over P1 equals to V1 divided by V4, all raised to the power n. Okay, so this means that we need to determine the value for, if we have V1, we know the value for V4, we know the value for P1, P4, then we can find the value for n. So let us move some steps back. Okay, so let us determine the value for V1. So how do we determine the value for V1? Okay, let us consider state 1 to 2, process 1 to 2. We know V2, but V1 we don't know. See, here we know V2, but V1 we don't know. So, but we know this is bounded by a polytropic situation. Okay, so for, isothermal process. And for an isothermal process, process 1 to 2, so now we want to find V1, find V1. So consider process 1 to 2. So this gives me, and since this is polytropic, isothermal implies P1 V1 equals to P2 V2. So my V2 equals to P1 V1 divided by P2. So this gives me 115 divided by 415 kilopascal times the mass, the volume, V1. Be careful over here. We know the specific volume. So specific volume, absolute volume V1 equals to specific volume V1 times the mass of the ideal gas. So this gives me mass of the ideal gas is 0.22 kilogram times the specific volume, 0.12. So this gives me 0.12 meter cubed per kilogram.
V2 or V1, sir?
What?
V2 or V1 we want to find. V1, right?
Let me see. Oh, sorry. It's V1. It's V1. I'm very sorry. So it's V1 we want to calculate. So this should be V1. Very sorry. So let me delete. Okay. So we are interested in V1 instead. So V1 equals to P2 V2 divided by P1. So then this gives me, yes, so we have P2 and the final, P1 is 415 and P2 is 115. So I'll have 115 divided by 415 as usual. Then multiply by 0.22 kilogram of the gas times the specific volume. Okay, so, and again, here, yes, the specific volume V2, has been given. Okay, so specific volume V2 was given, and if we want to calculate the absolute volume, V2 should give us the specific volume V2 times the mass. So this gives us, in this way, we have 0.22, okay, kilogram of the gas times 0.12, 0.12. 0.12 meter cubed per kg. So now if we calculate this carefully, okay, then we will determine V1 to be 0.00732 meter cube. Okay, so now, given that we know V1 already, now let us determine, let's say, let us determine the W23. Okay, so here, oh, very sorry. So let us find V3 instead. So V3 and V4, they are the same. For V3, if we look into this diagram, V3 and V4 are the same. But we can easily calculate V3 because we know that the work done from stage 2 to stage 3 is by isobaric constant pressure process. So let us consider process 2 to 3. And this is isobaric. Isobaric is constant pressure process. So the boundary work for the constant pressure process was given in the question. We are told, let's see, the constant pressure, the boundary work is this 0.525 kilojoules. So we can take advantage of this and calculate the unknown parameter. So we have W23, which is the boundary work. This gives me pressure. The final volume is V3 minus the initial volume, which is V2. Okay. So now we want to find V3. V2 we know already. Okay, so V2 is known already. So now we will see that, but we are told this equals to 0.525 kilojoules. So if you substitute the pressure inside, okay, so which pressure are we going to use? So here, P2 is the same as P3. Okay, so the pressure is given P2, which is equals to 115 kilopascal. Okay, so V2 also is known already. So from here, we can easily, so V2 absolute volume V2 gives us 0.22 times 0.12. Okay, so this is in kilogram. This is kilogram per meter cube in this way. So if you put all the substitutions, then we are left with V3. So V3 comes out to be V3 comes out to be equal to 0.525 25 divided by 115. Okay, so plus 0.0264. So eventually V3 gives us, so V3 becomes equals to 0.03097 meter cube. Okay, so now we have determined V3. So now we can easily use this equation now, seems to me. Okay, so V3 and V4 are the same. V1 we know already, P1 we know already. Okay, so the final pressure, P4, I think is also known already. Yes, P4 is also given. The final pressure, 0.262 bar. Okay, so we can use this equation to determine the value for N now. Okay, so we will have a situation like this, that P4 divided by P1 equals to V1 divided by V4 raised to the power N. So we have 64 divided by 415 equals to, let me see. Oh, sorry. It should be 62, right? Not 64. So 62. It should be 62. Okay. So 62 divided by 415 equals to 0.00732 divided by 0.03097, all raised to the power N. So if you take log and other things, so N becomes 1.3182. Okay? So now we want to determine the boundary, we have already found the value for N. So now the question goes on to say, let's see what the question tells again. We want to determine the value for N already, then the network of the cycle. So network, I've told you again, W net equals to W 12 plus W 23 plus W 34 plus W 41. Okay, means how do we determine the W41? W41. And so far we know W, and let me see, W12, the isothermal work input. Oh yes, so we have to determine that. W12 equals to P1 V1 log of V2 divided by V1, because that's isothermal. So if you calculate this carefully, okay, substitute everything into the equation, you have 415 0.00732, okay, times log of 0.0264 divided by 0.00732. So eventually, this gives 3.895 kilojoules. So W23 is constant pressure process. We know already. So now let us determine W34. W34 is constant volume process, which means this is isochoric. And we know that constant volume process 34 equals to P V4 minus V3. So V4 and V3 are the same. Okay, so in P, it implies this equals to 0. So W34 equals to 0. So the final one is to find W41. W41 is the polytropic process. And that is P1 V1 minus P4 V4 all divided by 1 minus N. If you substitute everything, you have minus 3.5124 kilojoules. So W net again gives us all the sum of all these quantities. Okay, so you sum, let's say, this plus 0 plus 3.87, okay, 3.87, then W12 is given also already. Okay, so then eventually we have, let's see over here. So this gives me 3.895 plus W23, 0.525 plus W34 plus 0, and then the last one minus 3.5124. Can somebody calculate this for us? Okay, so then this will be our last stop for today. So next week, I will discuss some questions on the application of the first law of thermodynamics. Okay, and then we will look its application for both closed system and open system. Okay, so from next week, I will not be solving the questions like this systematically. So I'll be jumping one question to another question. So I'll escape a lot of questions, especially in this slide, because we have a long way to go. We need to attend to chapter 4 as well. Okay, so next week I'll start with chapter 4 first, then the last part of 30 minutes, then we solve some questions. Okay, so is there any question so far? Can somebody give me the solution for the network? How much is this? How much? What is the solution? Let me see.
0.9076.
How much?
0.9076.
9076. Thank you. Kilojoules. Okay. So anybody who have any question? Is there any question so far? Let's see over here. If you have any question, please let us address the question now. Is there any question so far?
Sir,
Yeah.
for sample problem 3.6, the V1 is 0.07556, not
3 point what?
3.6.
You said what?
V1, not 75.56, but
You mean
0.07.
V1 is what?
V1 on sample problem 3.6.
Okay, let me go back to that problem. So very far. 3.6. So let's see. Sorry. Sample point. problem 3.6. This 3.8. 3.8. So it is disorganizing this thing. And let me see. Yes, so I've seen it. Yes, sample. This one, right?
Yes.
You said what is the problem?
V1 not 75.56 but 0.07556, right?
Oh,
Because divided by 2000.
oh, you mean V1
Yes.
equals to
0
0.7556.
0.7556.
Okay, okay.
0.07.
Oh, sorry. 0.07556
Yes.
meter cube.
Yes, sir.
Okay, thank you. So then the same thing here, right? So then what will be the final answer?
1.0794.
So I'll put again, cancel this, 0.07556 meter cube. So you mean the answer, the final answer is
1.0794.
1.94. Okay, thank you. Thank you very much. Okay, so any other question? Please let me know if there is any other question from anybody. Okay. Okay, if there is no question, then I think we will stop over here. It's almost time for, it's almost 6 o'clock. So we should